All right, so first thing first, we need to talk about sample means from normal populations. So in the previous section, we were taking sample proportions from categorical data, right? When you're in a category, you can say either you have blue eyes or you don't, or you have this color hair or you don't, or you have this type of car or you don't, or whatever, okay? You either are in a category or you're not. In those binomial random variables, we can get a sample of many, many, many p hats, and it forms a sampling distribution that can normalize. Now, if we start with a normal population, then clearly we're dealing already with a quantitative variable. And you take your normal population, create a sampling distribution, all possible samples of size n, the distribution of all the x, there should be a bar on this, all x bars. Okay, so I take the mean of every sample. It'll be normal as well. Okay, so if it starts normal, it'll end up normal, regardless of the sample size n. Okay, with the mean of my x bars being the mean of my original population. The sigma of my x bars shrinks by this square root of n. Instead of it being sigma, it's sigma divided by the square root of n. So this is basically my population, because if I just take one observation at a time, it's going to look like this, okay? And I'm getting spread out data, and the probability that I'm way over here greater than 66.5 is pretty substantial. But if I take 10 observations, the probability that I'm greater than 66.5 is this tiny little sliver, because the standard deviation has shrunk and it made my graph taller and skinnier. Okay, so let's look at this in action real quick, and then we can do a practice problem. Okay, so here is a parent population. I can adjust it, and I will in the next video. But if we start here, and we're going to take a sample of 5. Okay, so we'll animate a sample of 5. There's 5 blocks. Notice it's a little bit off to the left, but if you look at my sample, I got 2 from the middle. This one's close to the middle, and those 2 were both on the low side, and so that dragged my sample down low. I'm kind of surprised that it's that low, right? If I do it again, boop, boop, boop. It's funny, it's like it's pooping. Those are all right in the center. And look, it landed right in the center. And if I do it again, okay, there's my sample. I got a high one, and it's a little bit more to the right. Do it again. Okay, sample. Oh, that one's pretty spread out. Oh, but that one's a little bit on the lower side, so it's a little bit low. And do it again. Okay, if I do this many times, you see that we get this normal distribution, and it's skinnier than that. If I can do it many, many times, you see how like perfectly normal this is. Notice the mean of the original was 16. The mean of this got really, really close to 16. Okay, watch what happens if I make it a smaller sample size, only 2. Right, there's 2. I can be way over there on the left. Notice it was never that far to the left on the last one. Okay, but here, every once in a while, you get things that are off to the side. This one resembles this. It's skinnier, but not as skinny as it was with 5. Okay, or as it will be with 10. Look how skinny this gets. My standard deviation is now 1.58. Guess what? If I do 5 divided by the square root of n, the square root of 10, it's going to come out really, really close to 1.58. Okay, if I do this with n equals 16, 5 divided by 4 should be 1.25. So a single one is going to be probably close to this, but I might get something that's a little bit to the left or the right. There's a pile over here forming, so it might be a little bit left. Notice, so I got 18 instead of 16. All right, do it a second time. Here we're going to start getting data. We're over here. This one actually looks pretty good. It's centered at 15. Okay, if I do it 5 times, now I'm centered 11.37. I got some low ones. Wait, why is it so low? Is there one that's off the screen? I don't know. All right. Do this many times, and you start seeing very quickly the mean is exactly where that mean is, right? And that's where this is mu. This is mu of many, many x bars, right? I take a sample of size 16, calculate the mean of that, and that becomes a data point down here, right? Calculate 16, pick 16 things. Oh, I just messed it up from here. And then it'll take those 16 data points and create another point down here that gets added to this distribution. All right, so this is many, 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 many 40,000 x bars, and it's perfectly normal. Mean is exactly where that mean was, and the standard deviation is that divided by the square root of n. Perfectly. Okay, that's the big idea in this unit, when you have quantitative data that is normal, your mean and your standard deviation of your sampling distribution, the mean of my x bars is the mu of my population. The standard deviation of my x bars is the sigma of my population divided by the square root of my sample size. Okay, and I was adjusting my sample size, and you saw it getting skinnier and skinnier and skinnier because we're dividing by bigger and bigger numbers. So take a look at this. Weight of an egg, 2 ounces, standard deviation, 0.4 ounces. Okay, so we're looking at something like this. Here's my 2, here's my 2.4, and here's my 1.6. What's the probability that an egg will weigh more than 2.3? Well, I can do normal CDF, and we'll go from 2.3 to 999, and we'll make my mean be 2 and my standard deviation be 0.4. Okay, and do I have my calculator open? I'll open it, but I'll work on the next one in just a second right now. All right, so what if I take a dozen eggs and want to calculate the mean, the x bar of a dozen eggs? My n equals 12. So I'm going to take many, many, many samples of 12. So I want the sampling distribution where I'm taking the mean of 12 eggs, right? So this is somewhere around 2. This guy's got a normal probability somewhere around 2. Standard deviation of 0.4, standard deviation of 0.4. These guys are all normally distributed. They're all coming from this normal population. Imagine those 12 little dots dropping down below, okay? And we're going to be centered at 2 still, but now for an x bar to be over here would require 12 eggs all coming from the right side of this distribution, which would never happen. Most likely, you're going to have 12 eggs that are all centered around 2. And so my standard deviation, my mu of my x bars is still 2, but my sigma of my x bars is now 0.4 divided by the square root of 12. It has shrunk my distribution so that I'm way more likely, okay? Square root of 12, 0.4 divided by the square root of 12 is going to be a small number, okay? Divided by square root of 12. So this is going to be my standard deviation for my sampling distribution. Is only 0.115, okay? So this, which was less than 1 standard deviation away to get here, is almost 3 standard deviations away here, right? So we're looking here, 2.11 and 1.89. That's where most of my x bars are going to fall. These are my x's. This is a single egg. This is a dozen egg, okay? And so here we would do the same thing, normal CDF, but we would have to change the standard deviation, okay? So for this problem down here, it would have to become 4.4 over the square root of 12. So let's see. So the first one, second distribution, normal CDF, and we want to go from 2.3 to 999, where my standard deviation is 2, my mean is 2, standard deviation is 0.4, okay? So up here, we have an answer of 22.7% of the time. Okay? Down here, if I take the same thing and change this from just a 0.4 to 0.4 divided by the square root of 12. Now we're talking about the sampling distribution. This was a sample, or this is not even a sample. This was a single egg. This is a sample of 12 eggs, and so we're comparing it to the sampling distribution of a dozen eggs. And we find the probability is of an x bar greater than 2.3. That would be I would need a bunch of heavy eggs. That only happens, what did we see? 0.005. Okay, so good luck. We'll talk more about this in class. We'll create some of these on our own, and farewell.